Hey friends, welcome to a new episode of Calculuscious Explains It All. With me, Calculuscious, aka Mathy Cathy, also known as Jenny. That's right. Did you know my name is not actually Cathy? I'm sorry, I've been lying to you. It is Jenny. But Jenny doesn't rhyme with Mathy, and so Cathy it is. Okay, I need to give you a little warning before we begin. As you can see, I'm in my classroom again today, and there's probably going to be bells that go off. I have had such a hard time finding a chunk of time to sit down and record, and today I said, today's the day, and I just went for it. But, I know there's going to be bells that happen, and we're just going to roll with it. I'll see if I can, edit them out, but I probably won't. Okay, I'm just that lazy. I probably won't. Yay! Okay, so this is the series where I claim to explain all of everything, but I actually don't. What I do is explain hopefully just enough of something to pique your interest. And I am so excited about this episode because in this episode, we are going to talk about, wait, let me get it ready. We're going to talk about integrals. And I am so excited because basically integrals are the love of my life. Okay, when I thought of this series, almost a year ago, I was like, I should do this thing called Calculuscious Explains It All. I right away could not wait to make the integrals video, and I was like, I should just make it right now. But I didn't. Okay, I waited until I was ready, and now is the time. Bells and all in the school. Here we go. All right, take a look at this. That's weird looking, right? But do you remember in elementary school having a problem like this where the directions were find the area? And what did you do? You counted up all of the squares, right? And in this one, maybe the green squares are supposed to be whole squares. The yellow ones are very close to whole squares, and the pink ones are close to half squares. And you add all that stuff up, and that's an approximation of your area. Now, why am I talking about an elementary school area problem? Well, because actually, this is what we do when we find integrals. Yeah, we do elementary school area problems. Kind of. Okay, but with functions and curves like this. So if I have a function over an interval, I should be able to find the area under the curve. Now, when we say area under the curve, what we really mean is area between the curve and the x-axis over that interval. The question is, how do we do that? Because we do not have a formula for area of a shape like this. Well, how we do it is we draw shapes that we do have area formulas for, like rectangles and trapezoids. Now, if you have seen any of my other Calculuscious Explains It All videos, you know that I usually like to go to my man Steve Strogatz to explain the conceptual side of things, okay, because his writing is always so good in doing that. But for integrals, I actually love to go to this thing, and I can't remember who wrote it, but I'm going to click on the page and it'll say, I think, yes. Carl Hahn wrote this, and I just think it is one of the best ways. It's just a story about Kepler. Okay, some of it's made up, but it's one of the best ways to describe integrals to students who are just starting out. So I will put a link to this site in the description of this video, and I really suggest you check it out. Okay, but basically the story is about Kepler on his wedding night being fixated on a wine barrel and how to approximate the volume of the wine barrel. Okay, that's what he was thinking about on his wedding night in the reception. And so, his first strategy was to stack manhole covers. You know what manhole covers are? Okay, in my school, I say, do you even know what manhole covers are? Because we're kind of out in the country here. But we talk about it for a while and we get a good understanding of it. Okay, and there's a little figure here that you can refer to. But those manhole covers could be stacked to approximate the shape of the cylinder. And then a manhole cover is like a very short cylinder, right? The wine barrel is not actually a cylinder. So the manhole covers are stacked to approximate the shape of the wine barrel. but the manhole covers are very short cylinders, and so you can find the volume of those cylinders by using our volume of a cylinder formula, which is up here, V equals pi r squared h, and then you can just add all of those volumes up to approximate the volume of the wine barrel. Okay, and then a little bit later on in the story, they talk about, well, how could we make that approximation more accurate? How could we get a better approximation of the volume of the wine barrel? Is there anything else we could use besides manhole covers to approximate the shape? And what Kepler came up with were paper discs. So if we have paper discs of varying radii, we could stack those to approximate the wine barrel shape. And, we could take the volume of every single paper disc, add them all up, and there you have it. You have a very good approximation of the volume of the wine barrel. All right, so the key thing to take away from this is that a definite integral, okay, that's mostly what we're going to focus on here at the beginning. A definite integral is calculating some kind of area measurement, or you can take it into 3D and talk about volume measurements, okay? But, obviously because we're in calculus, we're going to try to make that exact. And the way that we're going to make it exact is with limits. Okay, here's one of the best quotes from that little story. But imagine taking the limit as the thickness of the paper goes to 0 and the number of paper discs goes to infinity. The limit of that sum, if it exists, would seem intuitively to match the volume of the wine barrel exactly. And that limit is what integrals are all about. Oh my gosh, I love that sentence. Yes, that is what integrals are all about. And so then, what we do starting out in this unit is we talk about drawing shapes underneath curves, because right now we're talking about volume, but we can take that back to area, and we can talk about drawing shapes under curves to approximate the area under the curve. And one of the first things that we talk about in that section are what we call Riemann sums. Riemann sums, oh my gosh, I didn't look it up ahead of time, so I can't remember the pronunciation. I want to say Riemann. Riemann it is. Okay, it's Riemann sums. I'm so bad at these things. Okay, so Riemann sums to approximate areas are where you, I'll go to that in a minute, are where you draw rectangular shapes using either a left endpoint of a little interval or a right endpoint or a midpoint on the interval to, get an approximate area under the curve. And they're pretty fun to do. And this little Desmos app is really nice because you can see all different kinds of Riemann sums and something called a trapezoidal sum, and even somebody added to this a parabolic sum, which we call Simpson's rule, to see how, when you change certain things, like changing it from drawing the rectangle from the left or the right or the midpoint, or changing it to trapezoids, changes the estimate on the area, and it's super fun. So I think I will try to put a link to this in my description of the video as well, if I remember. And you can see fun things like this. Watch, we'll just do a left Riemann sum, which is we call that an LRAM, rectangular approximation method. Now, I have another one over top I should turn off. We want to turn that one off. Okay, maybe not. I'm not going to waste your time anymore with that, but you can see it's pretty cool, right? So cool. You're going to love it. All right, and, whenever we do that, there is this element of finding a sum. You're finding the area of these rectangular regions, and you're adding them all up. And so, as, the author said in the writing, the limit of the sum is what defines the integral. So what I have here is the definition of a definite integral. And I love to teach this because it has some super fun notation that I've referred to in the past. I don't know if you can spot what I'm talking about, but maybe you do. And we talk about, where do all these parts come from? So, whenever you are finding the area of a rectangle, you could think of it as taking like the length times the width, or I like to talk about it as taking the height of the rectangle times the width. And the height is, from the x-axis up to the function. The width is how far you're going along the x-axis. And that is actually right here in these pieces inside your sum. F of c sub k is not a dirty word. That is to show the height of your rectangle. Delta x is to show the width of your rectangle, and they are being multiplied together to show that you are finding the area of that rectangle. Then what do? You add them all up. That's what this thing is, right? Our sigma. And then how do you make it an exact area instead of just an approximation? You get more and more rectangles, or if you're doing like the volume of the wine barrel, more and more really short cylinders, and that gives you an infinite amount of them. So you take a limit. Sometimes you see this definition with some sort of limit as the width goes to 0. But in this case, it is the limit as the number of pieces that you have goes to infinity. And that's it. That's your integral, okay? But if you know anything about integrals, you know that that's not really the symbols that we use to show integration because we have this different notation. Oh, but first, okay, yeah, here's the notation. But first, I think it's time for a meme, don't you? All right, yeah. This is one of my favorite memes because, again, integrals are one of my favorite things. Slash the roof of area under the curve. This bad boy can hold infinite number of f of x of I delta x in it, or an infinite number of area in it. So, to ruin the meme, I'm going to talk about it here. It is, referring to the fact that underneath this curve, we have these rectangles. And if we want to make the area approximation an exact area under the curve, what we can do is make the number of rectangles be infinite. That also, by the way, makes every width of the rectangle 0, or infinitesimal, we should say. Okay, but once again, this is not the notation that we typically use for integrals because Leibniz changed the integral notation from Greek to Roman, just as he did for derivatives. I think I said that right. I've been teaching for so many years. Why can't I pronounce things? Okay, but here we go. So now I'm ready to write something. All right, so what we typically see when we're looking at an integral, and this is called a definite integral because it has an interval attached to it. Okay, I'll talk more about indefinite integrals a little bit later on. But what you're seeing here is the integral symbol, okay? And we just usually read that as the integral of. And if you have numbers on your integral, and as I said, that means it's called a definite integral, that is the interval that you are working over on the x-axis. So this is your interval, but we also call the a the lower limit of integration, and the b the upper limit of integration. And going back to the integral symbol for a minute, I just kind of love this. An integral is a sum, okay, but we can think of it as an infinite sum. And so the integral symbol kind of looks like an S, right? Okay, it looks like an elongated S, though, like a longer S, because it's an infinite S, or an infinite sum. Yeah, I don't know if that's true or not, but I kind of like to think of it like that. All right, finally, here you have your function, or you can call it your integrand, what you are integrating. And the dx here comes from the delta x, okay? It's an infinitesimal, and, we can call that the variable of integration as well. Okay, so just some parts of the integral for you to know as you work with them. All right, so now let's work with them. Like, you may be at this point, hopefully kind of have an idea that an integral is like the opposite of a derivative, or they're related somehow, right? Or, I know that my students have already talked about, before even studying integrals, they've talked about antiderivatives. So the question is, how does this all tie together? Like, where do antiderivatives fit into integrals? Because there is, somewhere there's that relationship. Okay, so I want to show you a really simple example of how you can sort of prove why you use antiderivatives to help you with integrals. The directions here say use area to evaluate the integral. Okay, and what we're looking at is the integral from 0 to b of x dx. Okay, what do we do with that? Well, okay, our integrand is x, and that's our function. So what we're looking at is where b is greater than 0. So I can just sort of sketch my first quadrant of the coordinate plane. I'm looking at the function y equals x, which, has a point at 0, 0. And it also has a point at when x is b, y is b. And I'm finding the area of this, this region. Which is a triangular region, right? So the area formula for a triangle is 1/2 base times height. All right, so we can call this the base of the triangle, and hey, let's call it b, because that's, it's from 0 to b, so there we go. And this is a right triangle, so we can call the other leg the height. Okay, but we could also call that b, couldn't we? Because it's from 0 to b. So we could change our area formula to 1/2 times b, or 1/2 b squared. Now that's the answer, by the way. 1/2 b squared is the answer. The integral from 0 to b of x dx equals 1/2 b squared. Okay, but I want to remind you of something. 1/2 b squared, really b was just an x coordinate, right? It was this far on the x-axis. So I'm going to change it back now to an x, and we could call that 1/2 x squared. And look at what you have. You started with the function y equals x. And just by doing a simple little area formula and some rewriting, you ended up with its antiderivative, 1/2 x squared. And this is just one example of this, but there's all sorts of other examples that you can explore, and some of them we do explore in my class, where we start with something, we work through an area formula, and what we end up with is the antiderivative of the function that we started with. And so, yes, you can say that when you are evaluating an integral, you use a definite integral, you use an antiderivative, okay? Or, when we start to talk about indefinite integrals, that's basically all you're finding is the antiderivative. It's so fun. Oops. Okay, so a little bit more about when you evaluate a definite integral, you're using the antiderivative. Okay, there's something called the fundamental theorem of calculus, and there are two parts to the fundamental theorem. Okay, this part is what tells you exactly how to evaluate any definite integral. Capital F stands for the antiderivative of lowercase f, and so this part of the theorem says what you can do is you can take the antiderivative evaluated at b minus the antiderivative evaluated at a, and that will give you the area under this curve over the interval from a to b. Okay, it's like fundamental to understanding calculus. I think you can see that, right? So it is something that you're going to work with a whole lot. Okay, the other part of the fundamental theorem of calculus, it looks weird, but it's actually a very simple idea. I'm not going to touch on that now, but I will do a video about that, and you learn that, as you work through integrals yourself. Okay, and then once you have all of this background of areas and Riemann sums and all that stuff behind you, what you start to move into are all different kinds of rules and formulas and really fun ways to figure out integrals, to figure out antiderivatives and all sorts of things. And that's the part that I truly love about integration. There's so much to learn that you're never really truly done learning, in my opinion. You'll see, you think you know a lot, and then you see one that you have absolutely no idea how to do. And I mean, you can't just look at it and figure it out like you can with most derivatives. You really have to sometimes dig deep and try to, find methods that you aren't even aware of to answer the integral. And you might think that sounds horrible, but I love it. Oh, and hence this meme. Okay, so what you're seeing here is the difference between differentiation and integration. Okay, differentiation, you start, you apply your rules, and you're pretty much done, right? You have so many rules to learn, and once you learn them, you're good to go. Okay, integration though, as you can see, it is a little bit messier. There's all sorts of things to know. And as I said, once you think you know all the things you need to know, there's more things that you actually could know that, for whatever reason you didn't learn, because there's just too many things to learn. But again, that's one of the things I love about it, because I love to learn. So, I can always learn new things about integration. Okay, and it kind of makes sense that integration would be more difficult, because it's like differentiation is tearing down the function, or, I actually like to use the analogy you're squeezing it, but integration is trying to put it back. Like, think about like a tube of toothpaste. Okay, you can squeeze the toothpaste out of the tube very easily, and you can see what's in that toothpaste, right? But can you put the toothpaste back into the tube? I mean, you can try, right? And you hopefully will have fun doing so. All right, so now let's talk about some of those fun things you can do here. So, if you're looking at an indefinite integral, notice there are no limits of integration here. That is where you're just trying to find the antiderivative. Like, what do you take the derivative of that gives you 6x squared cosine of x cubed? Okay, what function do you take the derivative of that gives you that? And you could think about that for a while and try it. I encourage you actually to do that. Think about it on your own and try it. But I'll tell you, sometimes students struggle with something like this because they see two pieces and they say, oh, well, can I do some kind of rule? And it's like, no, not, I mean, yeah, but there's like a lot of different rules you could do. So you got to recognize which rule you could use. It's not just one straightforward rule. Okay, so what can we do here? Well, if you ever see a composition of functions, meaning I see cosine of x cubed, the first thing that I do is I think about what is the derivative of the inner function. The derivative of x cubed is 3x squared. Okay, so I'm seeing a variation of that over here in 6x squared. It's close to the derivative of the inner function, right? It just differs by a constant. And that means that most likely what you can use to answer this question is called U substitution. And, U substitution is sort of where you use the letter U to stand in place for things like this. I'm going to rewrite the integrand so that the composition of functions part is first, and then the 6x squared is in the back here with the dx. I'm going to let U equal the inner function. And so I know that this part will become cosine of U. But the question is, what does this stuff become? Well, differentiate this equation with respect to x, du over dx equals 3x squared. And then your goal here is to move the parts of this equation around and maybe do some other little manipulation to try to make it match, try to make one side of this equation match what I have underlined up here. So I can move the dx to the other side. I can multiply both sides by 2. And now I know that this stuff right here is going to become 2 du. So my u sub looks like this. This is the integral of cosine of u. That u looks weird. Oh my gosh. Times 2 du. Now, really what we're doing, there's this little property that says you can throw that 2 out there. Really, what we're doing here is we're just trying to find the antiderivative of cosine. What function do we take the derivative of and it gives us cosine? A sine, right? Our answer here is 2 sine of u. Now, I haven't mentioned this, and it's a really big part of integration. Not really, but kind of in certain ways. You always, when you're getting an antiderivative answer like this, you need to add what we call a constant of integration. We usually write it as a plus c, because if you think about it, c is just a number like 5. If I had 2 sine of u plus 5 and I took its derivative, that would be, 2 cosine of u, because this derivative of the constant is 0, right? So you always have to add that little constant in there. Final little step here, we change u back to x cubed. And there you have it. Here's your answer. So, you can check this for yourself. One of the fun things about getting these answers is you can then easily check them by saying, okay, let me take the derivative of this and see if I get that. And you would, because of chain rule. Okay, the derivative of sine is cosine. The derivative of x cubed is 3x squared. So this is really like u substitution is doing chain rule backwards. Oh my gosh, so much fun, right? Okay, I am not going to go over this entire example, but I will tell you that, u sub is just, as I said, one of many methods that you could use. It doesn't work every single time. Let me tell you why it's not going to work for this one. It's not going to work because what I see inside of my sine is just an x, and the derivative of x is just 1. Okay, that doesn't help me when it comes to this additional x on the outside. So u substitution is not the way to go here. The way to go with this one is something called integration by parts, which is basically like doing product rule backwards. So fun, I know. And again, I don't really want to take too much time to go through that, but my point in putting this slide here is to show you that what I just showed you with u substitution, it doesn't always work. There's all different things that you can learn to help you figure out these, these antiderivatives or these answers to these integrals, okay? Eventually, you'll learn to do something called integration by partial fractions. There's, I didn't even put it on here, but there's trig substitution. Oh, as I've said many times, the list goes on and on of things that you can do to figure out the answer to an integral. And then all of the places you can go once you know integrals. Look at these beautiful applications. I'm going to be honest with you. When we talk about derivatives, the applications are my favorite part of derivatives. I think the applications are so much fun. However, when we talk about integrals, I think they're really pretty. The applications are really pretty, but they don't get me as excited as just learning integrals. Learning integrals and how to figure them out, learning all of this stuff and this stuff. Gosh, I just think it's fantastic. It's so fun. Okay, but again, here's a nice little list of applications, and I'm sure it's not an exhaustive list, but it's a pretty good start for where you can go with integration. Okay, actually, this is an example from economics, and that is not on the list, but yeah, it's even in economics. Oh, okay, I was like, where's my last slide? All right, finally, if for no other reason, you should learn integration to understand the memes. Okay, that is why you should learn integration. As a, oh, that bell. Okay, as a meme lord, no, I'm sorry, I am not. Okay, but as somebody who has made many memes, math memes, I will tell you that integrals have the best content for making memes. So, I've had ninth graders say to me, I desperately need to know what plus C means because plus C's in all the memes, right? And I'm like, you need to learn integrals. You need to come to calculus, buddy. What can I tell you? So, if you have no other goal, make it a goal to learn integration so that you can truly understand all of these fun memes and what they mean. Okay, everybody, that's my spiel on integrals. I had so much fun. I hope you stuck around for my rambling. I'm sorry. I am just so excited about this that it probably sounded a whole lot like rambling or yammering, but I hope you got a little bit out of this and that you're ready to learn more about integration. As usual, I hope this was helpful. Bye.